So then the question is, why not more? If we know coal-fired power plants are bad for the environment, and there are other alternatives at this point, if we say natural gas is cheaper, we could implement renewables, which are now cost competitive with coal-fired generation. Why are we not retiring all coal-fired power plants? And so there are a couple of reasons here. One might be that utilities and regulators might be afraid of relying totally on natural gas because historically those prices have been more volatile. We'll talk more about that next time. Um, Renewables are not ready to directly replace baseload generation. Remember, coal-fired power plants, it's cheap electricity. The plants aren't super flexible, so we turn them on and leave them on for a long period of time. They provide this stable source of electricity, or they can throughout the day, and we cannot say the same for renewables at this point due to their intermittency. But the third reason I really want to talk about and stress, and we're going to continue to come back to this towards the end of this class, is that retiring coal plants early could cause utility costs to increase, impacting prices for consumers and or returns for shareholders. So let's look at an example here. Let's say we have a 700 megawatt coal plant. Its capital cost is $750 million. It's financed. In other words, the utility that builds this power plant is not paying cash. It's borrowing the money. It has two choices about where that money can come from, either debt or equity. Let's look at debt in particular. Let's say this utility finances $500 million of the $750 million coal plant using debt. It means it's going to have an annual mortgage payment for the next 25 years of about $33 million. So let's say we get about to year 14 and natural gas prices get really low. And we have a president who is thinking progressively about human health and protecting the environment and tries to pass rules that make it more difficult for us to operate or more costly for us to operate. And we decide we want to retire the coal-fired power plant in year 15. So take a look at the green line and get a sense for how much of the $500 million worth of debt we will still owe on this power plant. And it's going to be in the hundreds of millions of dollars, right? Even if we get out to year 20 out of 25, we're still going to owe about $100 million left on our original $500 million that we borrowed. So what this is referred to is the potential for stranded assets. So some utilities have not yet paid back the debt they accrued when they built the plants in the first place, or when they borrowed additional money to improve the plants in order to meet increased environmental regulations. And so early retirements could add to the utility's fixed costs without increasing demand. So let's say a utility constructs new cleaner generation capacity while also paying the mortgage on the old plant that's been shut down. So Duke decides, we're going to get rid of our coal-fired power plants. We're going to replace them with wind and solar and natural gas. Now, this only applies in a case where they have not yet paid off all the debt on these older coal-fired power plants. But let's assume they haven't. Let's go back to our rate-making formula. Duke wants to come up with some sort of target amount of revenues to cover their operating costs, which would be their fixed and variable costs, as well as profits for shareholders, which are based on the value of their infrastructure. So let's say in a really simple case, before the coal-fired coal plant retirements, their annual fixed costs are $50 million, variable costs are $35. The value of their infrastructure is worth $250 million, and the rate of return is 7%. What's their target revenues? We can plug that into this formula, R equals C plus V times R, and we get an answer of their target revenues of $102,500,000. And so we could also take a look in a very simple case. Let's say how much would they need to charge customers in terms of a volumetric charge if they have customer charges that earn them about $40 million. So we can figure out what the volumetric rate here is, and we can get a volumetric rate of about 6.25 cents per kilowatt hour. So let's say they retire these coal-fired power plants then, and they invest in a suite of new, combined gas and solar and wind. And in a really simple case, just to give you an idea of what could happen, let's say the fixed costs go up because now they have still paying the mortgage payment on these coal plants, And now they have more mortgage payments on their wind and solar and natural gas power plants. So their fixed cost increased from 50 to 60 million per year. That means their cost of service increases. It increases from 85 to $95 million per year. And so now their target revenue should be higher. They should be technically getting every year, if they want to cover their cost of service and return on equity of 7% for the shareholders, assuming that the infrastructure doesn't change in value, which again is sort of a bad assumption here. They need to get $112,500,000 every year. So we can take a look at what their actual revenues would be if they don't raise prices, right? So let's assume that they're just building new stuff, not raising prices. The demand doesn't go down. They're still selling 1 billion kilowatt hours. They're selling it at a volumetric rate of 6.25 cents per kilowatt hour. They have customer charges that net them $40 million. So the revenues don't change. That's what their revenues were last time, but their costs do. Their cost of service went up from $85 million to $95 million. So we can plug the normal revenues in with increased costs of $95 million, and then we can solve for the value of R. And what we see here is that the value of R declines from 7% to 3%. So shareholders in this case, if the fixed costs for the utility increase and they don't increase prices on customers, shareholders lose money. And so what do we know that utilities can do then? They can increase costs on the customers themselves. So what we're getting to when we're talking about retiring coal-fired power plants early, which we need to do and we need to do quickly if we are serious about dealing with climate change, is that it presents a clear trade-off between the environment and economics, at least in the short term. Somebody's going to lose if we have invested a lot of money in infrastructure that we don't end up using. Who loses could either be shareholders or customers. It has to be one or the other, if not both. Okay, so that said, coal is probably going to go away in the U.S. It's more a matter of when, not if. I mean, we have not talked about, and I'm not going to talk about the idea of clean coal or carbon capture and storage in this class. I think we're a few years away from that being, at least economically viable. And so when it's economically viable, I'll talk about it. But right now, there is not a significant plan anywhere to implement that technology. And that doesn't mean that research into carbon capture and storage technology is not valuable. It's vital, likely. But we're not going to talk about it much in this class. So what about coal use in the rest of the world? And this is sort of related to carbon capture and storage. At this point, the foregone, it's sort of a foregone conclusion what's going to happen in the U.S. It's we would like utilities to get rid of their coal-fired power plants as soon as possible. We would also like to not pay a higher price for electricity, and unfortunately, we probably can't do both of those things at the same time. So that's a policy decision. That's a philosophical decision. It's a matter of making sure that the people that are most vulnerable, that can't afford to pay higher prices of electricity, are protected in some way. It's a very difficult challenge, and we're gonna think a lot more about how to solve that challenge towards the end of this class. But thinking about the rest of the world and coal use over the rest of the world, that is what is more likely at this point, because we're so far gone in sort of the climate crisis. If we were starting at the beginning, what happens in the rest of the world wouldn't make nearly as much difference. But given the fact that the Western world is in the United States and Europe has already contributed so much to the amount of carbon emissions we can put into the atmosphere without causing irreversible damage, we are at a point where what really happens in the rest of the world is probably more important than what's going to happen in the United States. In that respect, things don't look very good. Honestly, I mean, I think on paper, the plan to invest in so much new coal-fired power plant capacity in both China and India in particular, but other areas around the world as well, are really not pointing to an optimistic climate future. That it suggests that these countries are going to be relying on coal for a really long time. And so this brings us back to this issue of the environmental Kuznets curve. We started out this class talking about this need to get countries to not follow our lead, right? We do not want countries to follow the similar trajectory in terms of economic development of going through from pre-industrial economies to industrial economies where their emissions of carbon dioxide reach a peak, and then slowly, as they transition away from industrial economies to post-industrial economies, that somehow magically, their emissions are going to decline, and emissions everywhere will decline because no one will be in an industrial economy anymore. I think that's beginning to look more and more like a magical thinking. There's certainly hope in some cases for countries to skip ahead, to not follow this Kuznets trajectory. But certainly the evidence from planned investment in coal-fired power plants in India and China are worrying, to say the least. All right, so sorry to end that one on a sort of a downer. Next time we're going to talk about natural gas. So I will see you there.